kind of debated what I should talk about. So I've decided that I'm going to tell you about one problem, and this should serve as some sort of diffractive reading of what how I, as an experimentalist, and many people in my business see the problem of non-equilibrium. So I will talk about the dynamics of cuprates under an optical drive, and specifically the search of enhanced coherence and enhanced superconducting-like features in these materials under this periodic drive. And so I'll just offer some sort of broad introduction at the beginning, which will be very short, but then I will just tell you a little bit of where we are, where we started from, what the experimental results are in this business of driven superconductors from our group, and what the challenges are. You'll see there's a combination of theoretical and experimental challenges that we've been addressing. So just by way of introduction, I suppose this is as good a place to start as any. So I think it's fair to say that the physics of quantum materials, has involved a quest for ever more precise microscopic control of the microscopic parameters of the system. We've gone from basically growing new materials and searching for new materials to, 20 years ago, people discovered that you could try to engineer physics at the interfaces between different materials. There's a number of other methods that involve pulling and pushing materials. Nowadays, this twisting of van der Waals heterostructures, again, has given us new ways to control these materials. What we're very interested in is the use of periodic electromagnetic radiation to generate periodically driven systems. So it's a slightly different angle on the problem, but it really does have some interesting control. So this is now, so this picture is a caricature of a bilayer cuprate superconductor, YBCO, where you have superconducting planes. You have pairs of those in the unit cell. And then you have, and superconductivity starts in the planes and then is established in a three-dimensional pattern by tunneling between the planes. The reason why I'm saying this already is that what we're trying to do is to use, for example, periodic modulation of the position of certain atoms by exciting specific optical phonons in the system to try to introduce periodic modulations in these physics. And the idea is that this form of dynamical modulation can create effective Hamiltonians in some way that will give new properties on average. And that's the type of problem that we're interested in, rather than exciting electrons or something. Is really sort of coupled to the guts of the system, for example, by driving phonons, and have these periodic drives. So just a couple of words. If you're in the business of driving collective modes with light, you want to use radiation. And there's, of course, a number of excitations that you can couple to. I mean, traditionally, lasers have been, the use of lasers has been confined to this region, which is the EV energy scale. And this is mostly because of technical reasons. It's very difficult to, things don't laze very well in the far infrared. Things like to laze in the visible. And so it hasn't been easy for many years to generate light at longer wavelengths. But we and other people have put a lot of work into trying to generate high intensity laser fields that could couple to collective modes such as phonons or other sort of more important collective quantum effects in these materials. And so this is a picture of a laser lab, which nowadays, this is a complicated setup, but not an infinitely complicated setup. And we can generate light nowadays pretty much wherever we want at field strengths that are in excess of few megavolt per centimeter. So this is where the systems start responding nonlinearly, and that's really the basis for everything that that we've done and what I'm about to tell you. So there's really sort of a technical bottleneck that we've been trying to overcome over the years. So there's a lot of things that you can do. We started early on trying to simply switch lattice structures. This is sort of used to, this is depicting an experiment done in magnetoresistive manganites where you can try to switch bond angles and change between insulator and metals by driving a single mode coordinate. We've been working on ferroelectrics, trying to find ways to switch ferroelectricity or to induce ferroelectricity in materials that are close to a ferroelectric state. There's also a lot of work we've done in trying to switch magnetism in various materials in which you have, in a sense, strong spin lattice coupling, but materials in which, say, piezo-magnetic materials, in which small amounts of strain in equilibrium are already known to change magnetism. So we've been trying to sort of control that. So this was work done by Tobia Nova, who was my PhD student, and Ankit Disa, who is now come back to the US and joined the Cornell faculty. And we've shown that you can either take antiferromagnets and make them ferrimagnets in either direction, and more recently, you can take frustrated magnetic systems like yttrium titanate and turn them into ferromagnets at temperatures higher than what you would get if you, in temperatures higher than the thermodynamic transition temperature. There's also work done in topology. This is work that James McIver, who's now at Columbia with Andy and Dimitri and co. He has shown that by driving certain materials like graphene with circular drives, you can open topological gaps and find interesting flow case states. So there's really a lot of things you can do once you start driving nonlinear collective modes of systems, and you find exotic non-equilibrium phenomena. And each one of those is really, we've been pursuing a sort of stamp collecting kind of approach where we try to sort of show that there's a number of things that you can do, but each one of these areas of research present really both technically and intellectually really exciting classes of problems. So as far as I'm concerned, the most interesting problem to be looked at is the one that has got to do with periodically driven superconductors, especially in the context of materials in which the normal state above the transition temperature is not the one that you would expect simply in a BCS model, but one in which you may, a normal state that hosts precursor fluctuations of the superconducting state, whatever these may be, either anomalous Gaussian fluctuations or phase fluctuations or things of this nature. So in principle, the idea is that you have a material that you bring it up to temperatures that are higher than TC, and you would like to use periodic modulations either to control the pairing fields, things that bind the electrons together and form Cooper pairs, or simply that control the coherence between this, let's say, these bosonic quasi-particles and enhance coherence between pre-existing pairs. So that's kind of the general goal, although this is a very qualitative way of thinking about this. So this business of driven superconductors is something that has been looked at for quite a long time. It was known already in the 1960s that if you take a BCS superconductor and you irradiate it with microwave radiation at frequencies that are below the BCS gap, so these are frequencies that don't create many new quasi-particles, but they do excite the already existing, thermally existing quasi-particles, you can create a non-thermal state in which, say, the temperature of the quasi-particles is higher than it would be than what the base temperature of the system is. And so what was discussed in this pioneering theory papers and many papers that have come after that is that this non-equilibrium state in which the quasi-particles are hot is actually one in which both the gap, the critical current, critical temperature, and similar signatures of superconductivity can be found above TC. So this is one early example of a non-equilibrium state with a higher superconducting transition than what one finds at equilibrium. There's also a lot of other work. This is work done in Alan Heger's group back in the day, who did photodoping with UV radiation in cuprates. Work done in Ivan Schuller's group in San Diego, and there's been a lot of sort of attempts in the past to try to do these things. Yes, Victor. Yeah, that's right. Well, we haven't followed these protocols because we don't use DC. This is, remember, is a DC form of irradiation. So you can imagine an experiment in which you heat and cool in field, so to speak, in electromagnetic field. So, I mean, in principle, one could try to, but it would be kind of you would have to find some proxy of this type of protocol. But we can talk about this later, actually, because there's multiple implications of what you just said. So now let me zoom in. So there's this business. There's some work done in enhanced superconductivity. There is work that is in our group that is aimed at controlling, periodically modulating the low energy degrees of freedom of the system. We have looked at a number of systems that we've done a lot of this in some organic materials where we would drive local molecular vibrations, both in the dope fullerenes and in some charge transfer salts. This is not something I will tell you about today, but there's a lot of, some of the effects are some of the most spectacular effects that we found are in these doped C60 molecules, although the microscopics is not very well understood because there's a lot of sort of chemistry behind the non-equilibrium physics of these. We've also done work in the cuprates, and the work in the cuprates subdivides in at least two groups of experiments. Some experiments that are shown listed here on the left-hand side, where we use light to melt competing orders that suppress superconductivity in equilibrium. This is things like stripe ordered or things of this nature. So this is work that was done by our group, has been since then validated by two groups of people. This is Rick Averyt and Basov and the group in San Diego. And this is more recently a group in Tokyo who has now looked at a different set of materials. So this is, a reasonably well established and also not so surprising set of phenomena. You have something that makes your superconductor worse, you take that out, and your superconductor gets better. Dynamics and non-equilibrium physics notwithstanding. And there's a lot of other work, and this is what I'm going to talk about today, though. So the whole talk is going to be 60 slides on this. It's a bilayer cuprate superconductor in which a specific phonon mode is being driven to enhance, to provide signatures of enhanced superconducting coherences or correlations or fluctuations throughout a whole regime of temperatures where the material is not superconducting in equilibrium. So this is today's talk. So back to the slide that I showed you before, this is what the whole talk will be about this. Bilayer cuprate, there's this apical oxygen. This is an oxygen atom that the distance of which to the superconducting planes is very much connected to the superconducting properties of the material, and we're just going to be modulating backwards and forwards. Yes. Yeah, I don't know. Yeah, millimeter. Yeah. So basically, the experiment is going to be as follows. This is now your optical surface. The planes go in, so you polish the crystal like so. The planes go into, along the pointing vector of the light, if you wish, and the light field is resonant to this phonon mode and is polarized perpendicular to the planes. So there's basically this atom that goes to and from. So, I mean, there's a lot of theoretical and experimental evidence that shows that the position of this apical oxygen does influence superconductivity. I don't know, mercury cuprates, where this oxygen is furthest away from the planes, are the ones with the highest superconductive transition temperature, meaning that the orbitals of this, that the planes are the most two-dimensional, and the p orbitals of this oxygen don't really hybridize too much with the plane. Whereas materials in which this oxygen is very close to the planes are not, have a lower superconductive transition temperature. People, for example, if you look at experiments in under pressure, when people applied DC pressure, there's a number of interesting works where they correlated TC. Let's see, what am I trying to say here? where they correlated TC with the distance of the oxygen to the planes. And it's by applying hydrostatic pressure, people showed that TC goes up when the oxygen comes away and goes down when the oxygen goes toward this. So, there's at least qualitative some value in driving this apical oxygen periodically. So the second thing that I'm going to say, which helps me to introduce the first set of experimental data that I will show you, is that one of the signatures of superconductivity that we'll be looking for has to do with the, linear terahertz reflection when this is measured with terahertz fields with, this is not the pump now, it's just the way we probe superconductivity, will be to use a terahertz field polarized perpendicular to the plane. So if you look in equilibrium at YBCO 6.5, and you cool this material below TC, what you will find two features. You will find that the real part of the conductivity will show a gap, and as is known from the optical properties of superconductors, and the imaginary part of the conductivity will show divergent imaginary conductivity, which reflects the presence of a pole at zero frequency in the real part of the conductivity, because these two quantities are chromoscurely related. Most importantly, the 1/omega-ness of this imaginary conductivity is directly proportional to the density of Cooper pairs, or to the area under the pole at zero frequency in sigma 1. In our experiments, what we do we go above TC. Instead of cooling this, we excite the phonon. And these are the optical properties that we get. Rather than getting gapping in sigma 1, and this is something that we've started to study comprehensively only recently, and so I won't tell you very much about it, we don't really gap in sigma 1. There seems to be a dissipative part of this driven system, some excitations of quasi-particles. So the system in this particular, in the cuprates, the real part of the conductivity doesn't really gap, but the imaginary conductivity acquires pretty much exactly the same 1/omega divergence as the one that I observe at 0 degrees, at zero. So the acquired coherent response is if I optimize everything and I get the pulses that are large enough in amplitude and long enough in time. Once you've optimized all the parameters, you go to 100 Kelvin. You drive these phonons, and you find that you have a divergent imaginary conductivity, which is exactly the one that you observe in equilibrium at zero, in the zero temperature material.
Wait. So sigma 2 becomes quantitatively equal to sigma 2 in equilibrium depends on T minus TC. So this is
right. Well, at some point it saturates at low temperatures,
so
right?
This is basically and presumably at some point it saturates with your applied field.
That's right.
Also.
That's right.
So the statement is that the two saturation values are about the same.
They're about the same, exactly. And if you make pulses that are long enough, I mean, there's a parameter space for this to happen. But now there's also charge excitations of the second fluid, right? So.
Can I ask about Mr. Epson rule?
Right. I mean, this is that non-equilibrium. So I don't really know how to answer this I mean, if you think about it, you have two fluids. The temperature of think of this even in the Eli-Ashberg case. What would some rule tell you? Right, you'd have hot quasi-particles, and you would have presumably sigma 2 that diverges to a number that is either larger or the same than the one that you have below TC. Does that satisfy you?
No, but we can talk about it later. I mean, this is a theoretical problem.
I mean, in a sense, I think you need to introduce different bands in the problem, right? You have all these quasi-particles that you already had at finite temperatures. This is a complete speculation. I don't have a quantitative. Yes, Victor. Oh, is that right? Yeah. Yeah.
Let's discuss it.
But even in addition to this, as Professor Millis well knows, you really have to integrate these guys up to almost 1 eV to when you need to track spectral weights, whereas this is a very narrow. So in a sense, who knows? One would have to really do comprehensive work and follow these spectral weights, and then really start having a conversation. I mean, this is, what am I going to tell you? This is what we get, right? Which is different than what we see in other materials. So most importantly, if you now fit this data, now here I have the Drude model. You fit this data with the Drude model. I've only put the Drude model for one fluid. But imagine you would do this correctly. What you can do is you can extract sigma 0, which is the extrapolated zero frequency conductivity from these finite frequency optical response. And what you would extract, you can take this rho 0, it's sort of sigma 0 is the limit for omega that goes to 0 of the Drude sigma 1. You plot it as a function of time, starting from the experimental data. And you find that for this particular compound, for a short amount of time, the resistivity reduces by 3, 4, 5 orders of magnitude, depending on just a large, which on a linear scale looks as good as any superconductor that you would publish in a paper. So now, the important point, this is old stuff, old stuff, this is 10 years old. Stuff is that if you plot this change in imaginary conductivity or the emergence of this finite superfluid density, and you plot it as a function of temperature, this goes, if this is TC in YBCO 6.5, you get a scaling that goes all the way to room temperature, which is also what makes work, this is then raises the stakes when you try to convince people that this is what you're seeing. But be as it may, you can kind of fit the data with finite superfluid density all the way to transient superfluid density, all the way to room temperature and above. And this is scales well with T star, which is however that is defined, or something of order T star.
So Andrea, can you go back one slide?
Yes.
So in the region from 0 to sort of 2 picoseconds,
yes,
where sigma 0, rho 0 looks to be 0.
Yeah.
To dissipate, right? How should panel B on the left look?
What do you mean by panel B on the? Well, that doesn't really matter, right? Because here we are fitting. I mean, this is sort of here we're fitting the zero frequency. If this were all right, so sigma 1 will be flat. You'll have the second fluid that kind of goes up. Whatever. Let's say that the scattering rate is out here for the second fluid, and there's a big peak here. It's at zero frequency.
There's a big peak that appears transiently.
That's right.
And over after 2 picoseconds or something, that big peak goes away.
That's right.
But
that's
not
right.
Much happens in the 20.
That's right. And then whereas the second fluid will have its own scattering rate out there. And I mean, this is a little bit tongue-in-cheek, of course, whatever that means, right? But if you take, if you look at the sacred texts of how you fit this data, and then you would expect rho 0. If this was an equilibrium measurement, this is what rho 0 would be. So now I'm going to show you what we've been doing over COVID over the past 5 years. Yes.
Sorry, I think I got a little lost. So you're continuously driving. The time delay is just the probe delay.
You're driving it for, nowadays we drive it for 3 or 4 picoseconds.
Okay.
Yeah.
And then this is after turning off.
After turning off. Basically, the lifetime of this thing is about the drive. This system, unlike in other material, has no intrinsic rigidity. When I'm done driving it, this thing goes back to a metal. Yeah.
Oh, wait, but I thought the sigma 2 goes away, or it's still lit?
No, sigma 2 goes away.
So after 2 picoseconds of the drive is
yeah.
off, the resistance goes back to what it was and sigma 2.
That's right. I mean, this is these two things are the same.
Okay.
Right.
So this whole novel state only lasts for the time shown.
That's right.
And
that's right.
Time with the drive.
The reason why I'm showing this is that sometimes when you give a talk and you tell them sigma 2, people who haven't done these fits don't really understand what it means. Sigma 2 means zero frequency resistivity in equilibrium. Divergent sigma 2, all the way to 0 frequency. So now this is, let me tell you, so the first experimental question that one should ask, we're still not understanding anything here, but lots of things, apparently according to the referees, lots of things can give you these kind of effects. But what you should really like to see that there's very large diamagnetic response that is compatible with superconductivity in measured when you photoexcite the material in field, as opposed to first photoexciting and then applying a field. And so, oh boy, I'm sorry. So this is basically, just to those of you that haven't thought about this for a couple of years since you were in school, let me remind you what we're trying to see. So let's say you have a non-superconducting puck. You apply a magnetic field, you have a magnetic field, and the magnetic field just kind of goes through this with small variations. What we're looking for is a situation in which, as you cool or as you photoexcite the material, the field lines are expelled from the center of the material, and they are concentrated immediately outside. So I expect to have a reduction of the magnetic field immediately above and an enhancement of magnetic field immediately outside. That's what I'm looking for upon irradiation. And so I should try to find a way, I should apply a field to this, and then I should try to put some sort of detector here that allows me to diagnose the intensity of the magnetic field immediately outside the superconductor with 1 picosecond time resolution. And this is, part of the problem in this business is that you're trying to take things that are easily done in equilibrium and trying to do them fast. And so you really need to come up with all sorts of crazy contraptions. And so what we do is we thought that maybe the best way to do this at fast time scales would be to put a material that has a finite Verdet constant. The Verdet constant is what relates the rotation of an optical field with the local magnetization in the material. So this is the Faraday effect. So you can bounce a light field off this slab of material and measure the polarization rotation, and that will be proportional to the local magnetic field. Right, so this is, for the purposes, I mean, we're now doing it in all sorts of ways, but basically if you take a piece of zinc telluride and you apply a B field, you will get a polarization rotation, which is proportional to B according to this Verdet constant. So now let me show you how you could do it in equilibrium. This hasn't really been done. So first we calibrate the system. Now you go above TC, you scan your polarization rotation across the sample, and the polarization rotation doesn't change very much as you cross the sample. Now you cool the material below TC in field, you scan back, and what you see is what you want to see, right? This is because of the demagnetization factor below TC, the field lines are more dense here, and so you have an enhancement in this polarization rotation or local magnetic field. And here you have a reduction. In this case, we're looking on the AD plane, just to get a bigger effect. And so the field on a thin film, and the field gets completely expelled. I don't have time because I want to tell you other things. There's very beautiful experiments in which we come with a light field now, with a big, fat, visible light field. We destroy superconductivity below TC, and we study the dynamics of how this thing becomes, how the green becomes so, you know, all the obvious things are kind of working out. So now what we've been, you know, this seems simple, but it's 5 years of 4 people's lives and lots of money paid by Max Planck Society. So basically what we do is we take the YBCO, we cut it along the C, you know, we expose the AC axis for various reasons. In this specific geometry, we don't do experiments in which we pump here and we probe in the same position. There's just nonlinear optical issues when you want to do this, but we go immediately outside. And now what we want to see is when we pump the material here, we want to see an enhancement in magnetic field out here. So we pump here the apical oxygen, we look immediately outside the pump region. And what you see is this enhancement of the magnetic field outside. I'm only going to show you 2 or 3 things. I could give you a 2-hour talk with all the checks and the counter checks of why this really looks like a light-induced diamagnetic response, but for the purposes of this talk, I will leave you with just this graph. What you see is that you go from a situation by looking immediately outside, in which the magnetic field, if you measure here, the magnetic field sort of goes up and then it goes down. So this is really sort of the work of Sebastian Fava, Giovanni De Vecchi, 2 PhD students who didn't know what they were getting into. Gregor Iotze, who's now joined the EPFL faculty, and Michele Buzzi, who's a hero of experimental physics, who's a permanent staff in our institute, who have really sort of been setting up these things. The only thing I'm going to show you is that this is TC. The temperature dependence of this effect is broadly not inconsistent with what we observe for the optical responses. This may be different, but it goes away at 300 Kelvin. It's still there at 100 Kelvin, and error bars notwithstanding, it's not 100% inconsistent with what we observed. I can't say anything more. I mean, it's not clear that at room temperature there is this effect, but there certainly is a very clear effect at 100 Kelvin, 2 times above TC.
How big is that compared to the equilibrium?
Right, okay. Larger. Because you remember there's penetration depths, and you need to, the transient chi is minus 0.5, the extract, plus or minus 0.2. If we've done everything correctly, but I think this is, so it's a large effect. Okay, so now I'm done with the pieces of evidence. What you have is seemingly high conductivity for a short time and expulsion of magnetic fields. So this kind of ticks the boxes of something that is not just simply a trivial. If you took a piece of gallium arsenide and you would excite it and you generate some supercarriers that with no phase rigidity, you wouldn't observe this effect. So this is clearly a non-trivial state with which does to magnetic fields what superconductors do. So now I'm going to walk you through what we've been trying to understand this problem over the past 10 years or so. The first question, you remember the data that I showed you before was pumping at a single frequency where the apical oxygen phonon was. There was 2 PhD theses and a extremely, for this curve, this was, so Bia-Long Liu, who's now at PSI, built a source that enabled him to pump anything, any phonon, any position he wanted. He did experiments in which he would pump at all these frequencies, and he would probe down here where you find the superconducting-like response. He did the experiment 52 times over 5 years of his PhD thesis, and he showed that only here where the apical oxygen is, you get a finite, this is omega sigma 2. So a finite omega sigma 2 tells you that sigma 2 goes like 1 over omega. And this is what Andy was quizzing me on. You can see that when you pump this phonon, you get exactly, you recover exactly the omega sigma 2 that you get when you cool below 10 Kelvin. So under this circumstance, so the important point is this only works if you pump the apical oxygens. If you pump the other things, the barium mode, whatever, this doesn't happen, okay? So this first piece of information, which is going to be important. But now, what is the physics of nonlinear phonons? And I'm going to try to walk you through all the hypotheses that we made, started a long time ago. The first thing that we looked at was looking at simple phonon nonlinearities. Let me walk you through simple ideas of nonlinear phonon response. This is something I've talked about multiple times in talks, but this is so normally when you think about a phonon, the way you think about phonon spectroscopy, you look at the linear response of a phonon. A phonon is basically a spring, and so the energy will be something that has the energy of the spring plus the energy of the laser modulo multiplied by the oscillator strength of the phonon, this Born effective charge, and this gives you a damped harmonic oscillator, which you measure normally when you do linear response. When you do nonlinear response, and so when this laser field is very large, you also have a large anharmonic term, which is basically a sum over all ways to mix 3 phonons and 4 phonons. So if I'm driving now this phonon QI, which is no longer a normal mode at this point, there's a lot of couplings that are subdominant in equilibrium that become important once you really drive a phonon at very large amplitudes. So in the specific case of cuprates, you can make a number of assumptions to simplify because this is going to be, I don't know how many equations of motion to study this response. You can first say that we're only going to look at cubic couplings, so 3 phonon mixing terms. You can say that there's only 2 modes if you think about the problem as a driven mode and a second mode that couples to the driven mode. You end up only with this sort of anharmonic terms. You can say that the material is centrosymmetric, therefore the second mode has to be even if the first mode is odd. And so you end up with a pretty simple set of equations of motion in which to leading order, under all these assumptions, you only have to worry about this anharmonic coupling between my IR-driven mode and whatever Q2 mode couples to this. This is, by the way, the same term that gives you thermal expansion. So how you sort of, at lowest order. So now we have to think about how is the lattice going to respond once I drive this mode. And so the way the lattice responds is understood by writing the equations of motion for QIR and Q2 in the presence of this coupling term. And so if this is my driven mode, which in time will sort of behave like a damped harmonic oscillator, what I will have is that the second mode, which used to be green and now which is green, will be subjected to a force that is proportional to the square of the coordinate of the mode that I'm driving. And so it will receive a push and it will be displaced. So this is the equivalent of optical rectification. In laser optics, it's basically the same thing for coupled phonons. And so what you expect is that all phonon modes that are coupled to my driven mode in this way will be displaced whilst the first mode is being driven. And so what you will have, if this is time, this is the driven phonon coordinate, and this is the coupled phonon coordinate, you'll have a displacive response of the lattice, which will now form, transient crystal structures. So there's different crystal structures as the material is being driven. So this is how we started early on. You create a new crystal structure, which is not stable at equilibrium. You melt orders here. Maybe that crystal structure is a better superconductor. So now if you look at YBCO, all the, this coordinate, when you drive the apical oxygen, will be a combination of all the Raman modes of the system, which will, depending, each one of these modes will couple with this Q square Q coefficient in some way, and that will give you a generalized coordinate. You can further argue that QIR is a singly degenerate mode, and therefore only the AG modes will be the ones that participate in this coordinate. And under all these assumptions, we got together with Antoine and Alaska Subedi at the time, and we looked at free electron laser diffraction. We looked at a bunch of peaks, and we fitted. So we basically measured as many peaks as the unknown normal modes, and we made and we sort of looked at. So this was done when Alaska was working with Antoine at École Polytechnique at the time. We went to the LCLS and we measured all these diffraction peaks, and we also validated that no B2G modes were involved. And we sort of made the hypothesis for whatever the transient crystal structure of the system would be under the action of this driven mode. And the only thing that we noted at the time was that this apical oxygen was being moved closer, so in the wrong direction, or further, actually closer by approximately 3%. And then this had to be compared to the changes that one observed under pressure. And so, at the time, one couldn't do much better. But who knows? We don't understand cuprates in equilibrium. So this might be one of the contributions of what the transient state is. I repeat, you pump a phonon. This couples nonlinearly in Q square Q to a bunch of other phonons. As long as the first phonon is ringing coherently, 2 picoseconds, 3 picoseconds, whatever the free induction decay time of that phonon is, the crystal structure is now on average distorted. And maybe that's a crystal structure that is good for superconductivity. This was good enough to write a Nature paper. I really don't believe this is what's going on, but it was fine. Roman graduated, everybody was happy. Yes, please. Yeah.
So maybe your remark preempts this question, but just conceptually, the phonon you drive is at Q equals 0, so it's
That's right.
uniform. And the discussion here is about spatially uniform
Absolutely.
But once you have a nonlinear coupling, I can start with Q equals 0 and create two phonons whose momentum is equal and opposite.
Absolutely.
So how do I keep the drive in?
Okay, Q square Q doesn't do that for you. Because remember, QIR is at k equals 0. So square of that is at k equals 0, and that will couple only to Q2s. So this mechanism only generates, however, and now that's the rest of my time. This can't be the whole story, right? It's great, but with time, of course, each one of these experiments is one of those things, right? You need to go to the FEL and do the experiment and then pump it and measure it and calculate it. But at least so really this business, you're really trying to peel an onion. And because we're developing the methods as we go along, there's only so much we can do at any given stage. So now let's go ahead a few years and let's look at what other opportunities, also in the spirit of what Andy's saying. Yes. Yes. So you do a frozen phonon.
Well, it's actually renormalized interaction, connection between lattice distortion, which exists, and the superconductivity is a bit sketchy because nobody can tell you where the superconductivity comes from.
Yeah, that's kind of my question. So you don't think it's phonon driven, so that
well, I mean, at some level, if you do materials discovery, everything is phonon driven. You make a crystal structure, and then that's the starting point.
The statement at the statement at the time was that the experiment has produced a new structure, and for some reason, which somebody else is going to discuss, this new structure was more hospitable to superconductivity.
That's right, a quasi-static structure.
a static structure that's, I think the dynamics.
Precisely. The way we sold this paper to get Roman graduated was we're doing dynamical materials discovery. We basically generate, and then we go to a chemist and say, chemist, make me the structure. And bada boom, we're going to all become very famous because we've discovered now how to make a room temperature superconductor. That was kind of, which nobody really believed, but it was still an interesting way to think about this or other problems. Yes, Victor, yeah. In specific YBCO 6.5, no. In YBCO 6.6, which does host charge density wave order, that is part of the physics. Because you know that at 6.5, there's, well, I don't know about spin. There is a spin density wave, but there is not a very strong charge density wave in this particular. Oh yeah, I mean, other people check for me, but I mean, our collaborators in Stuttgart have been, and in Milano have been looking at this in extreme detail. So you know that it's actually at the beginning we said, okay, let's go to 6.6, let's melt that, and then let's induce the effect, and that kind of scales pretty well at 6.6, where the charge density wave is maximum. I mean, this is where all my problems started, when people stopped believing what I said, because whilst I was melting competing orders, everybody said, they're good for you. That sounds great. You're melting competing orders. But once you go away from that, then it's kind of harder. You really need to think here. So the next layer of this onion which is going to be yet not the final layer, is the following. How does, you can think about this problem. You have a driven mode, and then you have various tunneling modes. Remember, you're trying to, the divergent sigma 2 effect is something that is made up of Josephson coupling between the planes. And so the Josephson coupling between the planes in the bilayer structure, think of this as a molecule has two modes, two normal modes. One that is basically dominated by tunneling between the furthest pairs of planes, and one that is dominated by tunneling between the two planes that are close to one another. This is like an acoustic plasma, and this is like an optical plasma if you do the normal modes right. But by and large, this is the low frequency mode, which tells you about tunneling between, which is lower energies because this tunneling has lower energy, and this is the high frequency plasma. So one could ask the question, instead of doing how does this phonon couple with that, how does this phonon couple with this? At the end of the day, you have an apical oxygen that is modulating whatever the electronic structure is in the planes. And so this is going to mess with these guys. So we've teamed up with our friends at Harvard at the time. So Eugene Demler was at Harvard, he's now at the ETH, and Marius Michael, who was at the time a student at Harvard, he's now in Hamburg. And so what they did, they wrote down some equations, which to me they made sense. And they said, look, to leading order, the lowest energy, the first coupling you're going to get is one in which you're mixing three modes trilinearly, the QIR mode at linear order, the J1 and the J2 mode. But because these are three odd modes, this effect is identically zero at k equals 0, at q equals 0, and is only finite at finite q. Okay? And so they made a prediction, and they said, okay, if you write this, you have three modes, you're going to have three equations of motion, and you end up with something that laser physicists love and think about when they start on, which is the physics of a three-way parametric amplification effect. So what you have, if you write, this is the equation of motion for the phonon that I'm driving, and these are the equation of motion for the two tunneling modes. And so those of you that build lasers, I don't think there's many of you that build lasers, know very well that whenever there's a resonance condition that the IR frequency is equal to the sum between this Josephson plasmon and that Josephson plasmon, then you will have a parametric amplification. So you could use this guy here to amplify fluctuations in this mode and in that mode. So that seemed like an interesting thing to do, and also was very intriguing because unless you pump exactly at a frequency, which is the right one, which is where the apical oxygens are, by the way. So if you pump with a phonon here, you won't get anything. So that kind of seemed like something we So the problem there is that now you need to do experiments where you can measure odd modes, not IR mode, not Raman displacements, odd modes at finite momentum. So this was, again, another one of those sort of PhD theses. This was Alex von Huggen was a student with me. He's now at MIT with Nugedic. And what he did, he noticed that, I mean, this is known, but that if you measure the reflection coefficient as a function of time, you get a number of oscillations that are associated with the even modes of the system. Imagine you have a capacitor. You take an even distortion of a capacitor that will modulate the energy of the system, will modulate the optical constants, and will modulate the linear reflectivity. However, if I'm now breaking inversion, what I should measure is not the total energy of the system, but the second harmonic of the probe pulse as a function of time. So he did experiments where he measured as a function of time the second harmonic, and because the system is centrosymmetric, the linear reflection coefficient as a function of time gives you the Raman modes, and the second harmonic as a function of time gives you the odd modes. So this should give you information on all the odd phonon modes that you're pumping and probing, and all the Josephson plasmons which are odd, because imagine you have a Josephson plasmon, the current goes down and goes up, and so this will break inversion at finite frequency because there's a voltage drop when you have an inductor that oscillates at finite frequency, and that will give me a second harmonic component. And also, what's beautiful about this experiment is that there's no penetration depth mismatch. Those of you that don't know about this problem of penetration mismatch, I'm not going to tell you about it. But there's a lot of commotion these days about this problem. Here I can measure really exactly what's happening at the surface. So now, let's look for the. Come again?
What do you mean by mismatch?
So I'm not good. Basically, when you do the experiments in some situations, you're pumping over regions of the sample that is thinner than the one that you're probing. And so you need to solve Maxwell's equations, which apparently is very difficult to do, and you can't trust them, but to get the response. But in this case, you don't even need to do that. Okay. So now let's go. Let me walk you through linear and nonlinear phonons. When I pump at very small fields and I measure the second harmonic as a function of time, I get what I thought I would get, which is the linear response. These are the two driven phonons that I'm pumping, which is dominated by one. I will comment on 1 versus 2 at the end of the talk. And so you'll get the linear response. But when you go in the region where the light-induced superconducting state is found at 7 megavolt per centimeter, you get all these other modes that are being excited, and especially at this huge peak at 2 terahertz. And this is a peak which is in a region where there's no phonons, and it's exactly at the frequency where one finds this Josephson tunnel, the low energy Josephson tunneling mode. And importantly, this mode plus this mode, which you actually kind of made up here by fitting the data, the sum of these 2 frequencies gives you this frequency. So this is, broadly consistent to have a mode like this. Now, okay, so let's test. So this is all discussed in Marius Michael's paper that was written after his PhD thesis, and the experiments are done by Alex. So the idea is you pump a phonon here, it decays into this and this, some frequencies, right? It picks the momenta so that the sum of the momenta is 0, but the energy is set by this coherent scattering process. And so the idea is that you get this mode here. So the first thing you expect is that this is amplified exponentially as a function. So this thing scales exponentially with the amplitude of this. And this is something we've checked pretty carefully. And so here you find that experimentally now you can measure the growth of the low frequency plasma mode, or whatever that is, as a function of the drive. And this fits pretty well with the theory. You can also remember, and again, the question was, how do you know that these excitations are at 0 momentum? The Marius Michael's theory says that this effect should be exactly 0 Q equals 0, and it should be finite only at finite Q. So Alex did very careful measurements in which he measured the second harmonic emitted as a function of outgoing angle. And what he found is that every other excitation of the system is being driven at Q equals 0, except for this magic mode that gets parametrically amplified, that is generated at these 2 momenta here. And I will comment on the 2 momenta at the end of the talk. So this is also broadly consistent with an idea where you have this parametric amplification of the modes at finite momentum. And also, if you do, you can now sort of study the polarization dependence of the second harmonic, and you find that this amplified plasmon is really odd. I mean, it doesn't follow the flower of a phonon, which is a B1U mode that breaks a mirror twice a cycle, but it really has got nodes and does weird things, indicative of. And thirdly, unlike all these peaks that are temperature independent, this amplified plasmon scales, goes away at a temperature that depends on doping. And again, it's a temperature that is not inconsistent with the measurements that we did with optics and the measurement that we did with Meissner. So somehow this parametric amplification of the Josephson plasmons must have something to do with this state. Now I'm starting to think more about these time crystalline ideas, where you have sort of this oscillatory state that has some average properties. And again, we measure the 2 dopings, but this is broadly the temperature at which this effect goes away is broadly consistent with other measurements of T star. Yeah.
You're very close to your TC.
Yeah.
Very short-lived, or
I think no. Or we haven't measured carefully enough, but yeah. And remember, when you do these, I don't know. There's all sorts of things, like when you think about the way people do NMR measurements, you really need to excite something carefully, measure it carefully. We're just not at that degree of accuracy in the measurements. Which brings me now to the last problem that we're working on now, which I will summarize in 5 minutes, because, yeah, I'm sorry, there was another question. No. So let's, have we peeled enough? If we sort of now look at this onion a little more, is this enough? A phonon, 2 plasmons, amplification. There's also a theory associated with these that maybe could justify the appearance of the Josephson plasma edge. It turns out that, so I have a graduate student, Nilofar Taherian, that said, well, you really don't have just, I said, let's try to figure out this parametric amplification well. And what she said is that you don't really have 3 modes, 1 phonon and 2 plasmons. These are doped cuprates. They have a chains and they have the other modes. And so there's really two phonon modes, the distance of which is the same as the distance between this and this. So not sure that this is a bit of a mechanistic problem. This is the way femtochemistry is done. You just kind of peel away everything, but they're important to try to understand what's happening. So it turns out, this is what I tried to sell you before, the 3-mode mixing. You have 2 modes and you say, well, you have 2 modes, the sum of the 2 will couple to J1 and J2 and will give me this 3-wave scattering. But what Nilo said, she said, if you take now 4-wave interactions, that has a lot of things, including the fact that the square of the sum of the 2 modes has a component that goes at the beat note frequency, which kind of matches the frequencies down here. And so when you look at, and also, this is kind of non-elegant. This one kind of looks more elegant. You could imagine a situation in which you're driving 2 modes and this and that, the other term go like this. And so when if you now run the equations of motion and you look at the data, the simulated responses, and you compare it to the experiment, you can't really tell whether these are 3 or 4 waves. And as I will try to argue in the next 3 minutes, this is important. So what we did was, I remember we had a conference organized here at the Flatiron immediately before COVID. And Peter Armitage gave a beautiful talk about multidimensional spectroscopy as a way to tease different coupling mechanisms. So the way you do the experiment, you can do the experiment instead of pumping with just one phonon, like Ignoramos, experimentalist, would do. You can pump this twice as a function of time delay between the two, and you can select by using by using lock-ins in the right way, only responses that come from the combined application of these 2 fields. So what you're trying to measure are the correlations between excitations with this and excitations with that. And then you do a time-resolved second harmonic and you measure these amplified plasmas in the same way. So now you get a nonlinear signal, which is as a function of the time delay between this pulse and the probe pulse, and as a function of time delay between this and this. And so what's really beautiful about this is that you can Fourier transform this. This is done in NMR routinely. So what you can do is you can take the Fourier transform of these guys, you plot all these, and what you will get, for example, along the diagonal will be nonlinearities of the self-energy of a phonon interacting with itself. But off the diagonal, you'll get how a phonon couples to some, all the off-diagonal peaks will tell you who couples with what. This is hard to do, but it's amazing. And now you can kind of take these 2 spectra and you can say, well, what do I expect in the 3 and in the 4-wave mechanism? I'm almost done, guys. But I'm excited about this because I think this is really beautiful experimental work. You can now this is the 2D simulation for the paper that we wrote. And this is, and we wrote with Alex, where we said this is 3 waves. This is the 2, which has some peaks in places where you don't see, which you don't see experimentally. And this is a simulation of the 4-wave excitation with the excitation of pairs of plasmons. So it turns out that this is baloney and this is true probably. What's very beautiful about this, it's 4 waves and not 3 waves. There's kind of this excitation. This is a pair of squeezed plasma modes. So I would like to actually, as I was doing this, I would like to sort of connect back today, Andy. There's work in other materials in which the importance of squeezed phonon excitations on the possible activation of non-equilibrium superconductivity has been discussed. But if I had to put money on this, which I would lose in 5 years, but I would say that this is what's going on, or this is, whether this is really the mechanism for photoinduced superconductivity, I don't know. But there's pairs of plasmons that are that are squeezed at finite momentum that are being generated, and somehow they give rise to now the oscillations at this stage are no longer oscillations in the plasmon coordinate, but will be oscillations in the variance of the plasmon, which would be some combined mode of this. and this is something I put in this morning as well. This might even explain why, when you look at the reflection coefficient, the light-induced plasma edge is always at twice the frequency of the equilibrium plasma edge somehow. So there might be, this is, I don't really know, but this may be something that has got to do with the fact that we're driving pairs of plasmons close to k equals 0 momentum. So I'm done, almost. I'm going to tell you where we are. So what's going on here? Yeah.
Just all of the structure that you presented in the last part of this talk.
Yeah.
Does it rely on the existence of a Josephson plasma? So there's some kind of superconducting correlation.
Very good.
Therefore, it's normal.
Very good. The best data that I showed you is taken below TC, where I have a well-formed Josephson plasma. The connection between the existence of Josephson plasmons below TC and the resurrected Josephson plasmons above TC relies on a strong assumption, which is that pre-existing plasma, incoherent plasma fluctuations are there above TC and are being simply amplified and synchronized in the same way that you would synchronize pendula, Huygens pendula.
But I guess my confusion is that even normal levels have plasmons. So the question is if there's some special superconducting character of the plasmons which is required above TC to get this.
I mean, potentially, if you had a terahertz, so rather than a metal, let's take a semiconductor, a lightly doped semiconductor where I can put only few carriers to give me plasmons that are frequencies lower than the phonons, right? Then these physics would also manifest itself. The problem that I have is that these guys don't have the Meissner effect. So okay, let me answer in a better way. The elementary scattering mechanism is not unique to the superconductor. It just requires a certain level structure and certain couplings. So this thing is in itself, these oscillations are nothing except that this state also has zero resistivity and a Meissner effect. This time crystal here, whatever, however you want to call that, look with this huge, and that this occurs at a frequency which is the same as that observed in the same material below TC, which shifts with doping and which correlates with the Z. And the features of this oscillatory mode are the same as the zero temperature superconductor along the C-axis. So I hope this is, Okay, so have I peeled, what are the questions? Okay, what is this? This could be just a mechanistic thing that happened, or it could be related to superconductivity. How do these effects explain optical, electrical, and magnetic properties of the transient state? So is something similar also going on in potassium 3C60 and the kappa salts? I mean, everything that I've told you is entirely dependent on a very specific set of modes coupling to other modes and the Josephson coupling and this and that and the other. So it's really not so clear. Yeah, so this is where we are. I thought that this would have been instructive just to give you an idea of how these experiments are done, right? So we change our mind every 3 years, but then we, and sort of how, yeah, anyways. So I want to thank a few people. Let's see. Whom do I want to thank? Michael first, and Alex. We've done all these latest, the experiments where we saw the plasma being amplified in the first place. Michael Fechner, who's a first principle theorist who helps us understand which modes do what. Nilofar and Albert, who have done the multidimensional experiments. Albert has joined the staff at Brookhaven now, so he'll be back in the US. And Marius and Eugene, who have just sort of, over the past few years, have been really sort of a guiding light for us to just make sense of some of the basic things. And thank you for your attention. I'm happy to take questions. If you have some. Exciting talk. No questions?
Just think conventional superconductor. Why the high temperature superconductors?
Why do I do it in high temperature superconductors, you mean? Well, okay. I mean, in conventional, this would be like aluminum or something. Yeah, aluminum has sure. Aluminum has a few problems. It doesn't have an optical phonons, so they're hard to pump. It's a metal. You don't see them. You could take MGB2. We haven't found anything, but we haven't tried very hard. MGB2 is as simple as I can probably get away with, where you have some phonons that will couple to the band structure. Well, we didn't try very hard. I had a lousy student who wanted to graduate. So this is like a product of two bad things. Yeah, say that again. I mean, what we find is the only materials in which we find this are, we found it in three classes of materials, 4 types of materials, and they all have a large vortex Nernst effect above TC. So they all have signatures of fluctuating, unconventional fluctuating normal states. You know, I don't have anything positive to say, but it's anecdotally, that's what I can tell you. No, not yet. Temperatures are not great. I mean, for me, this is hard enough that going below 5 or 6 Kelvin, but maybe, you know, I can take a heavy fermion and have a transient state at 6 Kelvin. Who knows? That's a very good point, though. Yes, please, Victor.
You just mentioned from is associated with the structural equation.
Precisely.
Well, basically, what the inverters charge to the carriers, right? So it's an obvious question, but we thought about is any of the Johnson plasma lines or anything sensitive to the charge, V versus E, they distinguish, or maybe it's something.
Right. I mean, in general, what you're looking at are sharp modes with a quasi-particle background. So you have Drude plus Josephson plasma, which is great at 0 temperature because one is much bigger than the other. But once the superfluid density, when you're close to TC and the superfluid density of the quasi-particles is the same as the one of the superfluid, everything gets washed out. Now, I'm sure if you had a Rix contraption with sufficient resolution, you ought to be able to differentiate the two because you can look at selection rules. But I don't think the resolution is enough. Remember, 1 terahertz is 4 millieV. So to go down to hundreds of gigahertz resolution, I just don't see current Rix probes being good enough. But yeah, that's all I know about this.
So I think I understood in kind of the first mechanism that you had this transient period where you had like presumably a different structure.
Precisely. Well, we know this from X-rays that there is a different structure. Yeah.
So in the kind of second mechanism, is there a way to understand like how long you can drive?
Well, okay.
Go back to some equilibrium.
I mean, of course, remember this is a driven dissipative system. So you have now this coherent state, which may be synchronized in this and that and the other, and then you have quasi-particles and all sorts of junk that is scattering left and right. And so the first part of the coherent response, will be basically determined by the inverse line width of the driven phonon. So the coherent lifetime, we'll have a ring down, and that's maybe 2 or 3 picoseconds. Of course, you could keep it simmered longer by using a longer pulse, right? But broadly speaking, it will only be there for the duration of the drive pulse plus a couple of picoseconds. The incoherent junk that happens may take a lot longer, have Auger processes and various things decaying. And so this is, I mean, there's these 2 aspects of this. And remember, the Eli-Ashburn mechanism relied on incoherent quasi-particles being at high temperature. So who knows, right? Maybe those quasi-particles are also good. But the coherences that we find here, I hope this answers your question. Yeah.